Good morning. I'm excited to share with you our work investigating what hematite, uranium, thorium, helium thermochronometry can tell us about fault mechanics in the shallow crust. The work that I'm going to share with you today is led by female USU undergraduate and graduate students. I want to acknowledge support from SCEC and the National Science Foundation, and I want to thank a number of collaborators who have been instrumental in this work. When I was asked to contribute to this session, what came to mind for me is what we know, and importantly, what we do not know about the mechanical properties and behavior of the shallowest portion of fault zones. And I remembered a really great talk at the 2019 SCEC meeting by Josie Nevitt, where Nevitt described observations of deformed grapevine rows and shallow geophysics and how they combined these data sets to produce models of fault slip for the 2014 South Napa earthquake. This detailed study, in many ways, is emblematic of the larger effort within SCEC to derive probabilistic earthquake hazard maps. There's a cornucopia of data and models that go into these maps, including our choices and assumptions about the slip distribution and rheological heterogeneities in the shallowest portion of fault zones and throughout the crust. And it highlights the need for direct observations of fault rocks to underpin these models. SCEC has powered many important breakthroughs in our understanding of the seismogenic zone that come from multi-scale observations of exhumed faults to complementary laboratory experiments that characterize fault friction, and even the development of geochemical and textural tools to take the temperature of faults to pinpoint earthquakes in the rock record. In today's talk, I want to focus on that shallowest portion of fault zones, in particular, the uppermost 1 kilometer and where faults are dissecting bedrock. And I want to leverage the mineral hematite, which is a common secondary phase in fault zones. And I want to show you how we can combine hematite textures and thermochronometry data patterns to quantify the timing, rates, and mechanics of fault slip and pinpoint deformation with depth. Hematite is amenable to uranium, thorium, helium thermochronometry. And this tool is sensitive to a range of crustal thermal fields. This is a pseudo-Arrhenius diagram with temperature on the x-axis and time on the y-axis. And what I'm plotting here are 90% helium fractional loss contours for different hematite grain sizes and with known helium diffusion kinetics. This diagram highlights the inverse relationship between the temperature sensitivity of an aliquot and time. Helium loss and our resulting hematite helium date depends on the thermal history and the grain size distribution of an aliquot, which we can characterize with scanning electron microscopy. Hematite is a secondary phase, and it occurs over a range of crustal conditions. This means that it can form at temperatures lower than or higher than its grain size controlled closure temperature. In fault rocks, this means that hematite helium dates can record mineralization or erosion, or even partial to complete helium loss or thermal resetting due to friction-generated heat or hydrothermal fluids circulating in fault zones. We have conducted hematite rotary shear experiments at the lower end of seismic slip rates and shown that asperity flash heating at localized fault mirror patches can generate appreciable helium loss from hematite. We have also combined hematite textures with thermochronometry data patterns to document small magnitude earthquakes at the upper end of the seismogenic zone on natural slip surfaces. In today's talk, I want to focus on new data from 2 fault zones, the Hurricane Fault in Utah, which is located along the eastern margin of the Basin and Range province, and the Painted Canyon Fault Damage Zone in Mecca Hills, California. The Hurricane Fault is a segmented seismogenic normal fault that is part of the Intermountain Seismic Belt and is capable of magnitude 7 earthquakes. We've been working along the Anderson Junction segment of the Hurricane Fault, where a meter scale fault mirror is exposed. This fault is dissecting a silicified Triassic conglomerate, and this fault actually extends for over 1 kilometer along strike. Locally, hematite adorns the surface in light reflective striated patches. We've examined these patches with a scanning electron microscope, and I'm showing you those images on the left. And what we see are different fault perpendicular hematite textures that vary from hematite platelets away from the fault to cataclysite as you approach the fault to bulbous aggregates right at the fault surface that we now know from transmission electron microscopy, or TEM, comprise 4 nanometer wide rods. TEM has also revealed the presence of partially amorphous silica right at the slip surface. Combined, these textural observations support extreme comminution and mechanical amorphization of the hematite and the adjacent silica-rich rock. This process is probably aided by fluids and a little bit of temperature. And so we're able to target these specific hematite textures for thermochronometry. Here I'm showing you our hematite helium dates in millions of years along the y-axis. This is a rank order plot, and each of these symbols are individual hematite helium analyses with their 2 sigma analytical uncertainties, and they are classified according to hematite texture. We know from independent thermochronometry and estimates of the amount of footwall exhumation or erosion that these dates do not simply record cooling ages. We can combine those independent constraints with our grain size controlled closure temperature estimates from our hematite to pinpoint these fault specific data to 300 meters depth. These data record post-seismic hematite precipitation, approximately 600,000 to 500,000 years ago, followed by co-seismic slip that induced helium loss associated with amorphization approximately 400,000 years ago. Because this deformation is so shallow, we know we are well above the seismogenic zone. And because this fault extends so continuously along strike, we suggest that it is recording the repeated up-dip propagation of earthquake ruptures. This is aided by mechanical and hydrothermal processes that are operative at the nano to micro scales that weaken fault materials in a comparatively stronger host rock. We can contrast our data from the Hurricane Fault with our work in Mecca Hills in the Painted Canyon Fault damage zone. The Painted Canyon Fault zone is a voluminous fault zone that is part of a positive flower structure, and the Painted Canyon Fault is inferred to intersect the San Andreas Fault with depth. Recent work has documented triggered shallow slow slip events following the Chiapas earthquake over 3,000 kilometers away. And this motivates our desire to examine the exhumed fault rocks to see how such slow slip events might be manifest in the rock record. Here, hematite occurs on millimeter to centimeter scale slip surfaces in dense networks, and it dissects Precambrian chlorite and clay-rich rocks. We see even at the nanoscale these perfect hematite platelets that are precipitating from fluid rock interaction with iron-rich clays. Many surfaces exhibit basal hematite injection veins, which have been invoked to occur due to fluid pressurization and may be due to slow slip events. We are able to extract hematite directly from these slip surfaces, and we target hematite and pre-screen it with the SEM prior to uranium, thorium, helium analysis to ensure hematite purity and to characterize our textures. Okay, here are our hematite helium dates. Again, this is a rank order plot. We have uranium, thorium, helium date in millions of years on the y-axis. Note that the scale is inverted and that there is a break in scale here. These colored squares are individual hematite helium dates with their 2 sigma analytical uncertainties. Some analyses yield larger uncertainties due to their low uranium content. For comparison, I'm showing you the available apatite helium data. The apatite helium data comes from the nearby host rocks, and this helps us constrain the ambient thermal history. This tool is sensitive to temperatures on the order of 60 degrees C, and it's helping us bracket exsumation through about 1.5 kilometers, depending on the geothermal gradient. We know from SEM work that our hematite helium aliquots have the same closure temperature as the apatite helium system. And yet, the vast majority of our hematite helium dates are younger than the corresponding apatite helium data from adjacent nearby rocks. And so what we see is that the hematite helium dates reveal mineralization events greater than a million years, but the vast majority of our data are recording mineralization events that are happening between 800,000 and 400,000 years ago. What's so remarkable about these data is their internal reproducibility at the sample level. And importantly, we see different slip surfaces within the same outcrop, so the same volume of rock, yielding different mean hematite helium dates. Taken together, these data point towards the Painted Canyon Fault Zone being repeatedly reactivated. Now, the textures that we observe on these slip surfaces are fundamentally different from the Hurricane Fault and from high temperature textures that we observe on hematite fault mirrors. The morphology that we observe, these high aspect ratio platelets, is reminiscent of textures from Painted Canyon Fault Zone clays and other phyllosilicate phases. And so this textural comparison and our prior hematite deformation experiments are motivating brand new deformation experiments at slow slip rates. What I'm showing you here is brand new data from graduate student Alex Demont. If you want more information, I encourage you to check out her SCEC poster 156. And so I'm plotting some of her hematite helium deformation experiment data as coefficient of friction versus the frictional rate parameter A minus V, A minus B. Her data are the colored symbols. For comparison, I'm showing you complementary data from phases that have similar morphologies, such as talc and clays, available in the literature. Now, these other studies are done on different experiments with a different apparatus, different conditions. And so, this is only a first order comparison. But the comparison is striking. Hematite has a low coefficient of friction, and we see that it is exhibiting broadly velocity strengthening behavior to approximately velocity neutral behavior at slow slip rates. More work is required to flesh this out, but it's interesting to note the similarities. And so we can combine our observations from natural slip surfaces with our deformation experiments to suggest that our hematite helium surfaces are capturing distributed deformation by slow slip events and/or creep in the uppermost kilometer that's happening less than a million years ago. We're able to pinpoint this deformation in time. And we suggest that these deformation events, these slow slip events, may have accommodated or even dampened radiated seismic energy from large earthquakes. And so to summarize, in some ways, hematite helium thermochronometry is like a deep time paleoseismometer. But I want to urge caution that hematite helium dates can have different interpretations depending on the conditions at which the hematite mineralized and its post-formation thermal and deformation history. We can interpret these data if we know something about the grain size distribution and the ambient thermal field. In these examples, we are revealing the structures and the mechanical properties that may promote the propagation of earthquake ruptures in one case, or the absorption of earthquake energy in another at less than 1 kilometer depth. And so it's the integration of natural and experimental work from slip surfaces, such as hematite slip surfaces, that can provide direct observations of fault behavior and slip rates that inform models of fault slip. Thank you. And with that, I'll take any questions that you might have.